The name of this video is Magnetic Flux. We will use this quite a bit in 342, in fact. Let's consider a single. In a future video, we're going to discuss multiple, these two in that case, filiform conductors or wires. So in this case, a single filiform conductor. Okay, as before, in a previous video when we have seen the ALBS in the filiform case. So the single conductor, we call it the region omega of space, capital omega. Let's sketch it here. And as always, we want to sketch the longitudinal axis of this conductor, which is right here. Like this longitudinal axis, we call it gamma. As always, if I pick a point here, capital Q, this cross-sectional area is the A, and from Q, this would be the L, which defines the volume the ADL or the LDA. As always, there's a point Q on it. So in this specific case, let's suppose that we have, for example, a current intensity with intensity I, which is a steady current right here. So there is a J, of course, associated with it. And as always, we can define with respect to any point, let's say a point here. We can define T as the normal unit, as the tangent unit vector at this point here, tangent to any point on gamma. Remember that the direction of T is, in fact, the same direction, is parallel to J. Okay, at this point, Q, if you want here. Okay, at this point, we call it Q. This point here. All right. So now we have a static condition as always. So we oriented this line gamma with the same direction as the current. So in this direction, which is counterclockwise. So in this case, for example, I could consider a surface, the surface right on the board, which has gamma as a border, the one I'm sketching, which is right on the board. So this surface here is one surface which we can call capital sigma associated with the border gamma. Remember the skiing trip that you can put when you go skiing? So you have this possible surface, but you can have also another surface like which has gamma as a border, which comes out of the board in this case, or on the other side of the board. In fact, you can have an infinite set of open surfaces of this type, capital sigma gamma, which are associated with one single border gamma, which is key for what we're about to do here. We already should know the answer of what I'm about to do, but now it's good to stress it a bit more. So if this is oriented counterclockwise, this means that the normal unit vector associated with this line, with the surface capital sigma and line gamma, points towards me, a right-hand rule, okay? So this is n associated with sigma, gamma, and this one is due to the right-hand rule, HR, in counterclockwise direction. So now we have all the bits and pieces we need in order to proceed with the rest of the problem, which is as follows. We want to find the flux phi associated with this surface capital sigma gamma. By definition, this is the integral, the surface integral on the open surface capital sigma gamma of B, the flux of B, of course, of B dot n, we call it n capital sigma gamma to be completely precise, dA, which is an infinitesimal area element, not to be confused with this one, is an area element here. Okay, let's not confuse them. There are dAs and dAs. In this case, that dA is what I mean, of course. All right, so now we know that B is a solenoidal field, so it can be written as the curl of A. So we can write this as the surface integral on this open surface capital sigma gamma of the curl of A, the vector potential associated with B, dotted with n. Let me drop the indices for simplicity. The A clearly is on this surface here, n. Now we can use Stokes theorem backwards. Compared to what usually we use it. And therefore, with this Stokes theorem backwards, we're going to obtain the line integral on the closed line gamma, which is the border of capital sigma gamma. This now is closed, of A dot TDL. Now let's remind ourselves what is T. As in the previous video, if this is T, actually we can call it T gamma if you want, let's put it in parentheses, and this is exactly the same as N if you want associated with sigma, which I can close like this. So we go from the flux through this surface to the line integral of A, which is quite nice because by means of this, okay, so this is just to remind ourselves that there are these definitions. Now, not to be confused, this N, the reason why I wanted to stress it because it's not the same as this N, but yet you can use Stokes theorem. So this T is the same as an N with this dA. Don't get confused between this dA, the N associated with it, the T associated with this point, or the N capital sigma gamma associated with this. So this is sigma and this is sigma gamma. But yet you can use Stokes theorem in this fashion. So the notation is a little bit cumbersome, but I hope now putting this in parentheses kind of clears up that this N is not this N. This is sigma gamma. And this DL, of course, is only on the gamma itself. So that's what you get. You get this beautiful result here at the end, which tells us that, incredibly, we can, given the vector potential associated with B, find the flux associated with that magnetostatic field B by doing the circulation of A. We don't have to do this compute the flux of B. We don't need to know anything about B. We can do the circulation of A. And this tells us two things. First of all, that it's independent, the flux, from the surface capital sigma gamma that I can use. I can use an infinite set of them. It depends only on the border gamma. That's the first thing. Second is super important. For example, in my field of research, which is Joseph-Sultana junctions, if you do not understand this, you will never be able to understand the so-called gauge invariant phase across a Josephson junction, which is an important concept. All superconducting quantum computing is based on it. And it's all based on this equation down here. So this equation is really absolutely important for many applications. In 342, we're going to use it in so-called Neumann integrals, which are useful to find mutual inductances and self-inductances, as we shall see though in 342, not in this course. So this is just a primer to what we are going to do with the vector potential. So to summarize this video, we wanted to understand magnetic flux. So a current on a line gamma, which is a filiform conductor, oriented counterclockwise. So this N associated with this line, with this surface here on the board comes towards me. And I want to calculate this flux of B due to this current. Of course, we know from the Ampere-Laplace Biot-Savart equation that this current I will generate a flux, a B field, which generates a flux. So this, of course, we can write as the curl of A, because B is solenoidal. But instead of doing this flux, we can go by means of Stokes theorem to this contour integral, okay, of TDL. Okay, and be careful with all the notations not to get confused between all these various T's and N's. Okay, that's why I was very picky here with that. That's it.